I have seen most of mechanical engineers learn the basics of DFMA, design for manufacturing and assembly, just after doing one or two real projects. Because in beginning, their design faces many manufacturing and assemblies issues, and they get continuous feedback from shop floor, like having sharp internal corners, having too much tighter tolerance, wrong bolting orientation, unnecessary larger fillet, and single part complex designing. But once engineers overcome these basic DFMA mistakes in their design, they stop improving further and they never truly reach a stage where their design are not just approved for manufacturing but actually optimized for faster and more economical production. And this is what we are going to learn in this video. I will share 6 advanced design for manufacturing and assembly tricks that only top 1% of design engineers are actually using. First is bolt sizing optimization. On screen you can see 2 vertical mounting designs and you have 3 seconds to spot the difference. 3, 2, 1. Looks exactly same, right? Now let me flip it. Now you may start noticing the difference. In the first design, all bolt sizes are the same. But in second design, the bolts used for vertical plate are larger compared to bolts used for rib mounting. And from a design point of view, this also makes sense because the rib plate is thinner, so the bolt size is selected accordingly. But now let's look at it from manufacturing point of view. So if you see the drawing of bottom plate of the first design, all bolt sizes are the same. So all mounting hole sizes are the same. So during machining, the operator can drill all the holes with one drill and all counter holes can be done with one end mill. But in second design, now the operator has to drill some holes with one drill size and then change the drill for the other holes. Same goes for counter bore holes. The cutter has to change again for different size. Technically, both designs are correct. But because of these hidden differences, first design can easily save around 10 minutes in manufacturing time. And if the quantity is 10 parts, that becomes more than an hour. We need to understand in manufacturing process, especially in machining process, most of time not spent in actual cutting process. Most of time goes in initial setup and tool changing. So the key takeaway is always try to reduce the varieties of the bolt size, thread size and dowel size in the same part. Now you might say that Ayush, in the first design, to keep the bolt size same, the ribs are made thicker. But in second design, the rib thickness is optimized based on load. So logically, the second design should be more economical. That seems correct, but in reality, the first design is still more economical because the manufacturer do not need to produce the multiple plate thicknesses. They can use a single raw material thickness, set it once, and machine all the parts from the same stock. So overall, it becomes faster, simpler, and more economical. So always try to minimize the variation in material sizes as much possible. Now the most important question is how do we actually decide the plate thicknesses? So whatever thickness we define in our drawing, that becomes our final requirement. But the manufacturer doesn't use the exact same size directly because the raw material is never perfect. It always has thickness variation, surface waviness and flatness issues. And as the plate size increases, their variation also increases. So what happens in practical is manufacturer always select a higher thickness of the raw material and then they bring it to the size using process like rough grinding, shaping and even milling. And after that they perform machining process. Now the raw materials are available only in standard sizes. For example, these are standard sheet metal thickness and these are plate thickness about 6 mm. Now let's say you define a plate thickness of 20 millimeter with a tighter tolerance. So the manufacturer must have to select the 25 millimeter of the raw material thickness. And then they will remove about 5 millimeter of the material just to achieve your requirement. And this is where the cost increase. So better if you could select 18 mm or 18.5 mm or go for 23 or 24 mm, then only 2 mm of material will be removed. Because we need to understand the material cost is way cheaper than removing the material. So instead of forcing to exact number, try to choose the thickness closer to the standard raw material thickness while still meeting your functional requirement. And this is real design mindset shift. You are not just deciding a dimension, you are deciding how much material is need to be removed. And now let's discuss some design for assembly tricks. Let's say we have a fixture, and to align it with the top tooling, we need about 10 millimeter adjustment in X and Y direction. So what most mechanical engineers do, they use two plates with slotted holes, something like that. So the plate can adjust the position of fixture in both direction. In CAD, this looks perfectly fine. But in reality, when you loosen the bolt and try to adjust it, the plate doesn't move purely in X and Y. It slightly rotates or deflects at an angle in very weird and uncontrolled way. So you never get a true straight adjustment in X and Y direction. So a very effective and simple solution is use a key, simple parallel rectangular key with counter hole. Fix the key with lower plate within a slot and provide an adjustment slot on the top plate like this. Now the movement is guided and adjustment stay precise without any unwanted angular deflection. It's not only for X and Y adjustment, even if you are use a single adjustment with slotted holes, use it with a key. Now the next improvement is shaft designing and their assembly. I have seen while designing the step shaft, even experienced design engineer forget to provide undercut at the shaft steps. Because in CAD this corner looks perfectly sharp, but in real machining the tools always has a radius. So this sharp corner will never be truly sharp. This is fine as per design for manufacturing. There is no issue in manufacturing. But because of this radius, it makes issue in assembly. The mating part cannot sit fully on flat face. Instead, it touches this small flat, especially with bearings or any other component that need to sit flat. And this can be completely avoided by adding a simple undercut at the step. So in manufacturing, the tools get proper clearance, and in assembly, it sits flat on any flat surface. And now, my most favorite design for assembly. Let's say you designed a cover for machine structure and you mount it with 4 screws at the corners. Now, to remove it, you have to completely remove all the screw every time. So instead, we can design it like this. Use a slot type holes with one large opening. Now you just loosen the screw slightly, slide the cover and remove it. Fast, easy and no risk of losing a screw. And if you can add a small embossed handle, it becomes more even user-friendly during assembly and disassembly. I can give you many more examples on design for assembly, but the core idea is when you're designing, not just think from manufacturing and functional point of view, also think from assembly and operation point of view, not only for bolted joints, but for all interchangeable components. A conveyor belt should be easy to tension and easy to replace. A changeover fixtures. Always use a proper locating pin and bosses and also quick bolting method. And this is it for this video. I hope you enjoyed the video. If you did, please give us a like and also consider to subscribe the channel, because now I think I will be more frequent on this channel. And thank you so much for watching this video.